All right.
Another building at ASU.
Can you guys see? I don't know what you guys can see. Hold on.
I don't believe that. He said that was right next to the ASU campus. Definitely.
Huh.
Not showing 5 times 12.
That's a bummer.
He works like 14 hours a day.
All right. Well. Huh.
Yeah. He's like, I really
should be. Oh, that's what it should be. Now I should be doing this.
He literally makes over $1,000.
Unfortunately, it's not working.
A year.
That's a bummer. All right. Well, I tried.
Like a ton of money. Is he a manager?
No.
Oh, yeah. Okay.
All right, folks. Well, you guys can't see it. Oh, at least you guys can see it. Fix that.
Over 85 bucks an hour. Like, how does that job? Why am I in school right now?
You're in school right now? What?
Well, because he was saying there's a construction worker that makes $85 an hour.
Yeah, you know what? The one type of person they don't want on a construction site? What? High school dropouts. It's not hard to pass high school, right? So if you didn't pass high school, you're not likely to be a very motivated worker.
I mean, you don't need a heart attack.
I mean, they don't really need you to use your high school skills, but. All right, we should have here a camera. You should be able to see online people. You should be able to see a very strange contraption. It looks like a swing. Miss Winter, can you see the swing?
Yeah.
It's on a slanty. So here's what I'm going to do here. I'm going to take this and I'm going to slowly roll this up. Slowly roll this up. Because I don't know how to do it fast. Okay, it's set up, ready to go. Can you guys sort of see it? Okay, I'm going to let go of it. It's going to simply go down. And then what happens when it gets to the bottom?
So you go back up.
Why? And I want energy.
Yo-yo.
It's like a yo-yo. What about energy?
Well, because it's carrying kinetic energy going down, and the potential energy carries. Oh, and nothing's left.
Potential energy?
No, I can't be the kinetic energy.
Kinetic energy, you said it's going to stop at the bottom. I mean, doesn't it actually stop at the bottom?
For a brief moment, yeah.
Well, if it stops and it's at the bottom, it has no energy.
So, well, nothing's left.
What energy does it have at the bottom?
Potential. Because it's not moving.
Is it not moving?
Work?
It's not moving velocity-wise, but it's moving some way, isn't it?
Heat and sound.
Heat and sound? Is it sucking heat and sound back in? That would be a better hypothesis than nothing. What is it doing at the very bottom? It's what? It's spinning. There's a spinning energy. We're going to call it rotational, but there's a spinning energy. When this thing gets to the bottom, it stops the normal type of velocity, but it still has spinning energy. In fact, oddly enough, your car, when it's on an inclined plane, is not frictionless because it has wheels. It's just storing energy in its wheels as you go down a hill. And that energy is energy that can keep you going.
So if it's frictionless, it's going to slide.
Frictionless, your wheels spin, you know that, right? And you slide down, right? So that you're transferring friction to spinning energy, which you can use later on to keep yourself going. Okay, so in this case, what you're looking at is the potential is being turned into kinetic. That kinetic is also being turned into rotational energy. That rotational energy allows it to come back up, not counting heat and sound. It doesn't come all the way back up, and eventually it dies. Strings, metal, not the best for that.
Is it RE?
No. We're going to use KE, but we're going to write a little ROT next to it. So we're going to, on the very front, on page 5-2, the back, rotational kinetic energy question mark. So how much energy does it have? We're going to use the analog. We're going to keep doing what we've been doing all along with rotational energy. What's the kinetic energy formula for normal? Mr. Vladi.
Oh, what?
What's normal kinetic energy formula?
That's half mass velocity squared.
Okay, so then what's the rotational form of each of these letters?
Rotational velocity.
Rotational velocity, which is our omega.
In radians, right?
And then what's our mass? No. We used it in brief. Inertia. Yes, rotational inertia. So here's my formula for kinetic energy when something's spinning. That's how I know how much energy it has.
So 1/2 weird eye thing.
Weird eye thing. This is our friend inertia, or moment of inertia.
Then work squared.
That's not work. That's our omega, so that's rotational velocity, right? So we're talking about the rotational form of mass times the rotational velocity squared. Right? It's just the same formula, but it's the rotational form of it. And that's what we've done all along. Now, I'll give you something weird to play with. What about work rotational? Force times distance. So we're going to try to make it analogous to force times distance. What's rotational force? Torque. And what's the displacement? Close. Rotation, we call it radians. It's just theta, right? So this is that formula. Now, honestly, this formula you're hardly ever going to use. This is the big one. You want this one. You need this one. Yeah? That's the one you want. Okay? With that in mind, go ahead and go to 5-8. Energy rotation. Start some problems. 1, 2, 3, 4, go. When I wrote that question, it was the fastest train. It was the fastest roller coaster in North America.
Wait, Mr. Rose,
Now it's not even the top. I don't know how many. Yes.
For this formula you gave us, are we ever gonna turn the KE into
Other flame. Yes.
and do square? We will do that.
You can do a spinning wheel can turn into kinetic energy. A spinning wheel can lift things. Spinning wheels can, or something can fall and get a wheel spinning. One half I omega squared. Two. When we are flowed by contact with a surface, how much heat would it make? In fact, that is the story of Montezuma's Revenge. They have a big spinning wheel down, they get spinning, and they just drop the train on it, launches it. And then when the train's going and doing its thing, they spin the wheel back up to speed again. So you drop another train on it.
Where is this from?
It's Knott's Berry Farm. Oh wait, not Knott's Berry Farm. Yes. Oh Lord, no, it's not Knott's Berry Farm. I'm wrong. It's Six Flags, Magic Mountain.
Oh, okay. Oh, that's what it is.
Yeah, and it's the roller coaster that goes like this. It goes. And then you go backwards through the loop, and then up like this, and then back in the station. And that's it, short ride. But it used to be faster than it is now. They slowed it down because they ended up with a tension problem over here. So they've decided not to see if the car will go off the tracks and launch and land in the park in the park. Yeah, they kill a lot of people. Yeah. I don't know what he's talking about. Moving on.
How about AW?
Okay, so here we go. Monsters Revenge arrived with a train at 12,100 kilograms shot from 0 meters per second and 30 meters per second in 4 seconds. It is propelled by a large inertia of 60,500 kilogram meters squared wheel. How fast would the wheel need to be moving if it comes to rest after launching the train? Energy before, energy after. Who wants this problem?
Me.
Okay. Let's put his hand up. Hand up. What kind of energy do you have at the beginning before the train is launched?
Potential.
Am I loading a spring? Am I going on top of a hill? What's launching this thing?
Maybe not on a hill, it's going down like that.
Yeah, no, it starts here at the station like this.
Oh, it does. Okay.
Yeah.
So kinetic energy.
What kind of kinetic energy?
Rotation.
Rotational. This big spinning wheel, it drops the train on the wheel, boom, it goes out the door. Okay, so that's K Erot. And what kind of energy it has after it's used up that energy?
I'm not sure.
What are you trying to get the train to do?
Stop. So
Not stop.
how fast would the wheel need to be moving when it comes to rest after launching a train?
Okay, so we're trying to launch a train. What's the train doing?
It's moving.
So what kind of energy?
Kinetic,
Kinetic.
rotation.
Just kinetic energy normal, right? It's a normal train.
So
Okay. So I'm going to go 1/2 I omega squared equals 1/2 mv squared.
Would the angular velocity be the same as just the normal velocity?
No, angular velocity is completely different, right? Angular velocity is how fast the flywheel is spinning.
So how do you find that?
That's what we're asking for, isn't it?
Like I said,
1/2. What's the mass of the train?
mass of the train is 12,100 kg.
And how fast do we want it to go?
We want it to go. It's going 7.5.
What?
It goes from 0 to 30 in 4 seconds.
So you just gave me the acceleration. I want to know how fast it's going.
30 meters a second.
Thank you. Right. That's how much energy it's got to gain from my flywheel, right? I got to gain 1/2 mv squared, where v is 30. Solve for omega. How about 13.4 radians per second? Not what you're getting. That's anybody's getting. It's a bad sign. What do I get for this?
I got 13.4.
13.4 was my units.
Already. Sorry.
Right like that.
I got 6 somehow.
Okay, come back.